When you've got multiple programs open on a computer, it seems like everything's running at the same time. For example, you might be working in a web browser like Firefox or Internet Explorer, listening to music on iTunes, and writing an essay with Word. However, under the hood, the programs actually run one at a time. It's the job of the operating system, Windows, Mac OS X, or Linux, to manage each of these separate processes, as the programs are known, and switch between them so that when you go from checking your Facebook page to working on your essay again, Word is the one that's running. Sometimes, though, we want programs themselves to be able to do multiple things like this too. If you're like me, you probably have a bunch of different tabs open in your web browser. One for email, one with a calendar, and so on. We could treat each tab as a separate program or process, like Google Chrome does, but many programs use a lighter weight version of a process called a thread. A thread is just another unit of processing, a set of instructions or code that can run quote-unquote concurrently with other threads. This is what makes it possible for you to browse Facebook while listening to me in the background, or to have two YouTube videos playing at the same time. So this general topic, known as concurrency, typically doesn't come up so early in computer science courses because the lower level details require a discussion of operating systems and the like. However, the programming language we use at the beginning of CS50, Scratch, provides some nifty tools to make it easier to write programs with multiple things going on at once. When you build Scratch programs, you're constantly working with threads. Each Scratch script, which is a code block that begins with one of the when puzzle pieces, can be thought of as a separate thread. Let's look at a simple Scratch program to see how this works. Here, we've got a fish object, or sprite, with two scripts that both start when we click the little green flag button. The first script controls the fish's motion. When the green flag is clicked, the fish gets placed on the left side of the screen, called the stage, facing to the right. Then, in a set of instructions that'll run forever until we stop the program, the fish glides to the right side, turns around, goes back to the left side, and turns around again. The second script controls the fish's thought process. It turns out that this is a hungry fish, so after waiting for 3 seconds, the fish will think, "I'm hungry," for a 4th second. This script also runs forever, and as we see from running the program by clicking the green flag, both scripts appear to execute simultaneously. The fish moves and thinks at the same time. Since the poor fish looks so hungry, let's add in some cheesy puffs for it to eat. Hopefully they won't disintegrate in the water. When we add in a second sprite, we'll also be able to add in scripts corresponding to that sprite, and hence there will be another set of threads that'll run. To give the user of our program control over when the hungry fish gets food, let's say that whenever the spacebar is hit, cheesy puffs appear on the stage for the fish to eat. Before we hit the spacebar, we'll want to keep the cheesy puffs hidden so that the fish can't see them. To do this, we'll need a couple of scripts for the cheesy puff sprite. The first script, the green flag, will just hide the food. Unlike the other scripts we've written, this one won't keep running forever. It will start and finish very quickly, right when we click the green flag button. The next script we have will wait for the spacebar to be pressed before executing. We can call waiting for user input waiting or listening for an event, and the code that executes when an event is received or heard is called event handling code. Our spacebar event handler will show the cheesy puffs on the screen so that the fish can eat them. At this point, everything's looking good. The next thing we need to do is to figure out how to get the fish to realize that there's food to eat. Let's add another thread to the fish that constantly checks whether or not it's touching the cheesy puffs. We do this in a separate thread, since that way we can constantly check for food. Otherwise, we'd only be able to periodically check for food in between gliding, turning around, waiting, or thinking. Okay, now let's run our Scratch program. As expected, the food immediately hides, and the hungry fish swims back and forth just like before. When we hit the spacebar, the cheesy puffs come into view, and the hungry fish says, "Woo!" But wait, that's weird. How come the fish's "I'm hungry" thought interrupts the other stuff? This is because we didn't establish any coordination between the 3 fish scripts. Each is running in its own thread, oblivious to what the others are doing. Let's fix this before we move on. Coordination between threads is a tricky task, since we don't have explicit control over when each thread runs or doesn't run. To send a message from one thread to another, we'll need to use a variable that we can set or write in one thread and read in the other. Let's create a variable called foodFound that we can set to true when the fish runs into the cheesy puffs. We'll of course want to make sure that we set it to false initially. Then, in the fish's thinking thread, we'll check to see if the fish has found food before displaying the I'm hungry thought bubble. Now, running the program again, we see that the fish doesn't get interrupted with thoughts of hunger when the cheesy puffs are out. The final problem we have is that the cheesy puffs don't go away after the fish quote unquote eats them. From the fish scripts, there's no easy way to hide the cheesy puffs, so we need to send a message to the cheesy puff sprite to hide itself. We could do this with another variable that the cheesy puff sprite has access to, as well as the fish sprite. However, there's a cleaner way to do this in this case, since instead of sending a message to a script that's somewhere in the middle of executing, we can send the message to a script that's waiting to start. We do this by having the fish broadcast an event, one we'll call eaten. Then, we'll create a script for the cheesy puffs that will wait for this event. This is similar to the spacebar event, except that this time, the user's not the one directly triggering the event. Now, all we have to do is set our foodFound variable back to false, and we can now give the hungry fish as many servings of cheesy puffs as it wants. So not too bad, right? In C, writing multi-threaded programs is more complicated, but the basics are the same. Anyway, I hope you have a great time building some fun concurrent programs in Scratch. My name is Nate Hardison. This is CS50.